But I mean, you guys might be disappointed because that's like, you guys could have done that as a project. So he took that idea. This guy who gave this apparently, I don't know, he's pretty, I don't know, Dr. Pam, the head of department, he knows him from somewhere, and he was saying he was really good, so that was good enough for me. Actually, it was pretty neat. When you have hardware, when you have RAID, and just because it's related to operating systems, I'll talk briefly about it. Anybody know what RAID stands for? No. Mainly because RAID is usually slower than it's sometimes slower, depending on what kind you're doing. You can do RAID. Like RAID 0 is just for speed, whereas RAID 1 is slower. But RAID stands for Redundant Array of Inexpensive Disks. So the idea is that you use multiple disks to create either redundancy or in some cases performance by using multiple disks in the place of one. So in this case, if each of these disks is, let's say it's like 100 gig each. Okay. Actually, let's say we had two. Okay. One kind of naive way to make these redundant so that you can lose one is just anything you copy to the first one, you copy to the second one. So that if you lose one, you'll have a backup on the other disk. Okay. RAID 5, when you go to RAID 5, that's usually for sometimes performance if you have fast enough kind of additional hardware, but often mainly for redundancy. If you have 3 disks, you can make all of them redundant for one disk if you save one of the disks and you put you save 1/3 of the disk space for parity information. So what you do is, if I want to store, let's say I want to store 2 bits of information. Okay, I want to store a 1 and a 0. What I'll do is I'll write across the disks. Okay, so I'll write a 1 and a 0. And when I write to the 3rd disk, I won't write new data. What I'll do is I'll write parity information. So in this case, let's say I'm going to do, my parity information is going to be XORing these two. So XOR these two, you get 1. Right? If I write another piece of information like 0, 0, XOR of this is 0. Right? If I write another piece of information 1, 1, XOR of this is 0. Right? And then I can finally write another piece of information with XOR. Okay? What's neat about RAID is that if you lose one of these disks, you can regenerate your information. And you do that by, if I lose this information because this disk goes down, okay? That disk, if I lose that disk, I can pop in a new disk, right? After the failure, I can pop in a new disk, and then I can do XOR here to regenerate the information. So 0 and 1 is 1, 0 and 1 is 1, 0, 0 is 0, 1 and 1 is 0. Yeah?
Why can't you have 2 different disks and copy them to anyway? Like, if you have 2 disks, whatever you put on the first one, why can't you put on the second one directly?
You can, that's RAID 1, that's mirroring. Do you see how this, for one disk failure, is, first of all, you can't do mirroring with 3 disks, right? But let's say you had another disk here, right? So you're saying, why don't you just mirror? And you can mirror. If you do RAID 1 mirroring on this, you just mirror that one to that one, that one to that one, or some combination. But that's actually that's fine. Okay, so you mirror, right? But how much disk space do you actually get if you're mirroring? Half. So in this case, you get 200 gig out of 400 gig, right? If you do RAID 5, you get 300 gig out of 400 gig. Because now you still do XOR. You still only need one of the disks, right?
But the XOR can only save 100 gig of data. So if you wrote, say,
Right, but your mirroring scheme can only save 200 gigs of data if they fail in the correct sequence. Right? If you lose 2 from mirror, they're all gone. Or half your data's gone.
but in that, the maximum amount of data you can have quote unquote completely saved, like,
It's one disk. You get one disk failure.
oh, okay, that's now.
Right? And in your mirroring scheme, you almost get 2 disk failure, but more than likely you get 1 disk failure. But you get 100 extra gig of storage in RAID 5 when you're not failing. Okay? So what he did was in this lecture that was on Friday, he gave this he made a scheme where how you lay out, how you choose, you don't just put data on here and then XOR. What you do is you lay out the data in a way where it ends up making a graph. Okay? It ends up making a fully connected graph. Yeah, just start it. Okay, so it ends up making a fully connected graph where you color it in a certain way. Does everybody know what graph coloring is? It's when you choose a color for each edge where no 2 edges next to each other have the same color. So you'd have like 0, 1, 2, and 3, and then you'd have, I don't know how you'd end up doing 0, 3. It's 2. Right? That's what I remember. This one's not numbered, right? This one. Oh, actually, I already colored this one wrong. Yeah, actually, there is an easy algorithm. I just don't know it off the top of my head. And he had a neat little algorithm. 2, that's where he colored 1, that's where he colored. Oh, book. Yeah? You don't? Oh, that's a 1. Yeah, I screwed it all up. What you do is, basically, he had a formula where it was, since they were a prime number of nodes, you could actually just do modular arithmetic and color them. But anyway, what ends up happening is, if you lose a disk, okay, what you can end up doing is, with the remaining colors, you should be able to find a path which visits each node, even the ones that aren't there. And if you can find the path, what you can end up doing is rebuilding the information on the missing disk by basically doing the XOR of the remaining paths. So if I lose a disk right here, right, and these all crash, right? All these lines go away. Okay? What you can end up doing is you can find a path through here, and at each node, you can use the XOR of the remaining solid lines to rebuild the other line, just like we did with the XOR before, right? So you rebuild that other line right here, right? And then this one you rebuild this other line. This one you rebuild this line, and then you can rebuild that with what you've rebuilt. And what ends up happening is that if you lose a particular combination of 2 of them, you can still rebuild the RAID set, even though you're only, with normal RAID, you're only allowed to lose 1. So by arranging the data in a certain way, you can still, you can reconstruct this information on losing 2 disks, but in addition to that, you're still just using regular XOR for what's called the parity. Okay? Most advanced RAID systems use a complex algorithm for this where you need additional hardware. So this was a kind of a way to get two-disk failure by just using a clever algorithm. Which if you use a clever algorithm, which you can do in software, usually it's very cheap. And your write and read speed is still the same. The only part that's slower is rebuilding the RAID set if one fails, which isn't often. It's a neat property. So something like that, I mean, that's kind of revolutionary for RAID. I mean, you can create two disks. I mean, basically what you're doing is you're buying, and I mean, it's like a free additional disk for anything that's using RAID. So it's pretty neat. And there are limitations to this because like there's limitations like you have to have a particular number of disks, and they basically have to be primes, or they have to be like 2n minus 1 has to be prime or something like that. There's like these different combinations of disks that you have to make the graph work. But if you have that, it'll work. And if you don't have that, you can actually use the next highest good number and then just pretend like the disks have failed, you know, so you can get down, but you're going to lose some space to parity. But, I mean, it was interesting. So it's neat that you can take graph theory and apply it to something like, I don't know, like RAID. Okay. So, last time, we stopped at this. Yeah, we stopped right here, talking about the effective access time, and this was for when using a TLB. Anybody remember what a TLB is for? Huh? Oh. You should still be able to tell me what a TLB is for, even without the picture. Kind of, how so?
It's
Does it store data that we need? Like, does that program data in it? Not a program. Pages and frames. So it's a cache for what? No. The page table. Okay. It's a cache for the page table, which lets us know what page is in what frame, right? It's a cache for the page table that's faster in what way? Why is it? How is it faster? This diagram should tell you. There is searching, it's just done in parallel. It's done in constant time. Okay? You look at every entry at once, and then one of them spits out. This is done in what's called associative memory. Okay? This is expensive, just like cache, right? It's more expensive than, you know, this is doing this kind of lookup is a lot of circuits. So this is expensive. They use it in a limited fashion. So what we store in there are basically page table entries. Which ones? Probably the ones that we've just recently looked up. Okay? So this lets us, when translating from a logical address to a physical address using paging, this lets us skip an access to memory. Okay? Because we don't go down to the page table to get the frame number, we go through the TLB, and if it's there, we get it in. This would be constant. Okay? Whereas normally, what do we have to do? We're not looking up a frame in the TLB. Where are we looking it up? In what? Page table. Where's the page table stored? No. Memory. Okay, so page table is in memory. Okay, we go and look for it, look for the page. That's one memory access. We get the page, we get the frame that we need, and then what? And then we go do our real memory access. Right? So we went to the page table to get the frame, and then when we actually get the frame, that means we have a real address. now we can go to memory. Right? The whole purpose of this exercise to begin was to get to memory. So we can't get around that we're going to have one memory access. But the page table is the second one. If we go through the TLB, right? We go through the TLB, constant time, and then our one memory access. Right? Frame, and then D is for the offset. But D is the offset. So, just real briefly, when translating from a logical address to a physical address, we're given a page number and an offset, which represents some page in memory, in logical memory, okay, and then an offset from the beginning of that page. When we go to the frames, you may not be in the same order, but this particular page is somewhere in a particular frame. So we take the same D and the frame, find the frame, and then go D offset. Right? That's how we get to a physical address. Okay? This is a quick way, this TLB, is a quick way to map from this P to this F. Normally, we just go to a table, look it up. Okay? Which one? This? Same. We're still doing the page table. This is a shortcut for that. Right? This right here is a way of kind of caching lookups to the page table. But the page table is this. This is an example of looking up, just regular looking up with a page table. Okay? But since this part right here, this page table is actually stored in memory, that's two accesses, whereas with the TLB you have one.
How is the page table searched? Is it just from top to bottom?
Well, there's different kind of approaches to storing the page table, because page tables, what ends up happening is they can get really big, and that means there's a lot of different approaches. But for example, if you have a page table that's like this, each entry, right, is the same size. You can do an array, so you could probably, you can do just random access by doing offsets. In other words, by basically an array indexed by page number. Right? Or you can do it other ways. But see, and we'll talk about this actually with some of the different schemes. This can end up being inefficient if you have tons of pages that are unused. If you have a sparse array, you'll be using up a lot more. No. These are the page numbers. These are the frame numbers. Okay? Because you're getting from a page to a frame, so you look up the page is the index, is your key, and your value is the frame. So an entry, 2-1, what is that saying? What is the entry here, 2, with the value 1 saying? What's that?
Page number 2, frame number 1.
Right. So that's saying that page 2, right? Page 2 is in frame what? 1. Oh. 0, 1, 2, IJKL, right, is in 0, 1, IJKL. These are how big the frame are. These are actual addresses. Okay. page 0, page 1, page 2, page 3, right? Page 2, 0, 1, 2, is in frame 1. Start numbering the frames from here, 0, 1. Same data, right? So, what would the D value be in these addresses? One of what? One of the letters, okay? But more specifically, it's an offset from the beginning. So, it's a number from 0 to 3. Yeah, 0 to 3, right? So if I give you the address, what letter is page 3 offset to? And where in memory is it stored? No. We're 0 based on numbering the pages. Page 3, and I said offset 2. Oh. The answer is O. Right? Okay, so, first of all, here's how you do it. What's page 3? Page 0, page 1, page 2, page 3. Offset 2, 0, 1, 2. Okay? 0, 1, 2. Okay? But, okay, so now I've said page 3, offset 2. Well, it's that letter, which is all well and good, but we need to get to physical memory. So, page 3 is frame 2. 0, 1, 2, offset 2. 0, 1, 2. Oh, it's the same thing. Right? Right. In the long run, it's easier. It's counting from 0. Okay, so everybody good with this? This is important. This is very important, this concept of mapping pages to frames, because what we're going to talk about next are different schemes of this. Okay, so we have that. TLB, right, is an improvement on this. In that, anytime we normally do the exact same operation looking up from the page table, anything that we've recently looked up, we put in here. Okay? Knowing how that TLB works should explain this effective access time calculation. Okay? Calculations like this you'll find throughout discussion of memory, caching, things like that. Okay? You basically look at the calculation as two different parts. Okay? You calculate how fast can I access whatever I'm accessing, in this case, memory. How fast can I access memory if my kind of improvement works? So in this case, what's our improvement? Yeah, the TLB, associative lookup. So, how long does it take to access memory with the TLB? Well, going in here and looking up takes how long? No, it takes a small amount of time. It's constant, whatever it is. Okay? So, this is what they're calling epsilon. Okay? But this is one of our times that we take. Then what do? Then we put this together and then we look up in memory. So that's one memory access time. Okay? Okay, so 1 is the memory access time. Epsilon, right, is the TLB lookup. What is alpha? What does that mean? What does hit ratio mean? Hit ratio is how often what we're looking for in the TLB is there. Does that make sense? I go to the TLB to find a page, and it's there. How long does that take? 1 epsilon. Right? So, if I hit it that much, right, as much as alpha, 1 plus epsilon, 1 plus epsilon times alpha is how often I access at that speed. Okay? Likewise, if we get a miss means we can't use our improvement. Okay? How long does a miss take? Two plus what? Okay, explain 2 plus epsilon.
Well, it goes to the TLB first.
Okay, so that's important. We go to look up in the TLB. Is it there? No, this is a miss. Okay? So, we get a miss. But how long have we taken to do that? No. Epsilon. Okay? So now what do we do? No. Yeah, we have to go to the real page table. So, where does the page table live? In memory. So that takes 1 memory access to go to the page table and look up a frame. Now we get the frame, and then what? We need to actually do our memory access. So that's another 1 memory access. So 1 memory access, 1 memory access, 1 epsilon. So, we all know 1 plus 1 is 2, right? So 2 plus the extra epsilon for the missed TLB. And then what is this value? 1 minus alpha. It's the miss ratio, right? If we hit and miss 100% of the time, alpha is the percentage of time we hit the TLB. The remaining is 1 minus alpha. That's the miss. Add all this together, and you get that. Do all that. It should work, yeah? Questions? Yeah.
Yeah. I'm confused on after 2 plus the epsilon.
Mm-hmm.
Because
What does that value represent? What does
okay,
2 plus epsilon represent?
That's what the confusion is. Because to me, 1 plus epsilon, no result. It couldn't find it.
No. It could find it. It's 1 plus epsilon.
Right. Okay. And miss ratio is there.
No, hit ratio.
Hit ratio, right? Then, if it's not found, then 2 plus epsilon. Why is 2 plus epsilon? There should be just 2. I know this is right, but
No. Oh, you're thinking we do both. We don't do both.
oh, okay.
That's what alpha is, and 1 minus alpha, right?
Okay.
For every time we hit with alpha, there's 1 minus alpha times that we don't hit. So this is total amount of time from start to finish, how long it takes us to get there with a miss. 1 plus epsilon is the total amount of time it takes us to get from start to finish with a hit. Don't think of it as I do this first and then I do that.
Okay.
right? They're each independent.
But how are they linked? That's what I don't understand. So if it finds it, then it's 1 plus epsilon?
Yes. One memory access plus the time it took to look up in the TLB. Right? 2 plus epsilon is epsilon, look it up, miss, go to memory for 1, then go to Let me just point out one thing. No matter how efficient we are with all of this, you at least have 1. Why do you at least have 1? Because the whole purpose of the exercise is to access memory, right? So we're at least going to have 1 memory access. What you're trying to do with TLB is trade 1 additional memory access for epsilon. In other words, instead of doing 1 additional memory access, I'm going to do a smaller amount with the TLB. Okay? But this is a way to calculate how much better do we get. In other words, if we say that caching only works some of the time, this is a way of quantifying what does some of the time mean. Okay? Because if we have a low hit ratio, we can end up doing worse than without using the TLB. How is that? Here's a question for you. What is the formula for doing this operation without a TLB? No. We do not use a TLB at all. It is not 2 plus epsilon. There's no epsilon. It's 2. The answer is 2, right? 1 memory access to go to the page table, 1 memory access to do our memory access. No epsilon involved. So, if we have a low hit ratio, the value 1 plus epsilon gets small, but the 2 plus epsilon gets bigger. And if it gets big enough, we're adding epsilon to our original constant, to our original 2 that we were doing without the TLB. Good? Moving on. Okay. Memory protection. The idea here is we're still doing the same. This is just kind of an addition on the page table idea. Is that if we're not immediately going to load pages into frames when the program starts, we might do it when we need it, right? If I'm a program and I need to access a particular area of memory, I can go look for it, but if it's not there yet, the operating system can load it, right? Or the chip can load it. So here's the idea behind the valid-invalid bit. If we have not loaded a page into a frame yet, then it's considered invalid, okay? So if I'm the program and I say I want to access page 2, what's the first thing I need to do? I need to look up the frame for page 2. So I go to the page table, I go to entry number 2, 0, 1, 2, right? And then I look up the frame 4, and then I can look for that in main memory, right? 0, 1, 2, 3, 4, and I can find my page in the frame. Okay? So, if I'm not loading all of the pages immediately, let's say I go to look up an additional page. I can go to, I try to look up page 6. Okay? In this case, we don't even have a page 6. Okay? So I go to the page table, which is the same size for any program, right? We give our programs a view of logical memory that is the same for everyone, normally. Okay? So I go to look up page 6, 0, 1, 2, 3, 4, 5, 6. Right? And then there's going to be a number there, but I have to check the bit to see if it's actually an allocated page or not. Okay, this is just a flag for the operating system to know whether or not that page does indeed belong to the program. Okay? I wouldn't worry too much about this. It's just letting you know, is there a page in there or not, and you can still have the same size page table for every program. Okay? Questions on this? It's just saying, yeah, there's a good page in there or not. Okay, shared pages. Okay, there's a very useful idea in memory management. Okay, shared code, okay, is a way of saving memory by not duplicating the same pages in memory. Okay, and by save pages, I mean if you are sharing a library with another program, you wrote your own program and it uses a particular library. Let's say use a particular math library so that you can do some complex calculations. Okay, another person writes a program and uses the same library. Okay, well normally if you load those programs into memory, you also load the library in so that you can jump to the code in the library. Okay, a clever thing to do with shared pages is any of the pages that represent the library that both of you used in your program, will make it the same page. In other words, the same page that you have in memory will be the same page that the other program has. Okay, in other words, we can just point you both to the same frame, and your pages are identical, so you won't care that it's a different program's copy. So, but they do have to be identical. So the idea here is, let's say I have multiple programs in memory. Process P1, process P2, and process P3. Okay? In this case, they're using ed1, ed2, and ed3. Okay? These represent, apparently in the example, they represent an editor. So all of these different users are using an editor. Okay? Now, an editor, no matter who's using it, will use the same code, right? If we're both running VI, it's the same VI for everyone. Okay? The only difference is that I might be working on a different document than you, right? Chances are I'm working on a different document than you. So we both have different data that we're working on. Okay? And all the variables and things that VI uses to do its job are different for us. Okay? So the idea here is I'll let each individual user, each process, have its own data segment, but in this case it's a page, one page, but the editor will be shared among all three. Okay? So this means in main memory, okay, all three of us can use the same pages or the same frames storing pages editor 1, editor 2, and editor 3. And then we each get our own page with data 1, data 2, and data 3. Okay? So total memory use, total physical memory use in this case is what? 1 page, 2 page, 3 page, 4 page, 5 page, 6 pages. Right? All three of us running uses 6 pages or 6 frames of memory, of physical memory. Okay? How much logical memory are we taking up? 12. Right? Each of us has our 3 editor pages and 1 data page. So 4 times 3 is 12. Okay, so what we've done is we've gone from using 12 units to the 6 units that we're using, which is good. It's half the memory. It's a free half of your memory, just by sharing the code. Questions on that? What makes this possible? What are some of the things that make this possible? One of them is the clever use of the page table, right? We have this page table here that is nothing but a pointer to a frame that belongs to a program, right? If we were doing this with contiguous memory, okay, with memory that's all in sequence, okay, we can't do this, right? If I allocate process 1 this is main memory.
At 1, at 2, at 3, and data.
Notice I don't draw lines because we're not paging. We're doing just sequential memory. Is there a way that I can allocate process 2 where I share the editor pages? I can't, right? There's no way that I can put all of this data in the same order for process 2 and not use up the additional memory. Okay? Here I can, mainly from the fact that page table frees us from having to do things in order. Right? Because we're pointing each page to a particular frame, and they can go in different orders, and they don't even have to be next to each other. We can scatter them about. Okay? Kind of as a side benefit to that, we can also do tricks like point 2 different processes to the same frames, using the same data in them. Okay? This should also illustrate another thing to you. Each process gets its own page table. Does everybody get that? It's very important because what it does is in an operating system, it lets the operating system give each program and each programmer the same view of memory. I just say, here, you have 4 gig to work with. Right? Just start from 0, numbered all the way up. And you can use it however you want. Okay, and all I have to do as the operating system is keep track of the pages and frames of them individually. So, what does this tell you about what happens during a context switch? What do we need to be sure to do during every context switch? Save what?
Pages.
Okay, well these are saved just by inherently being in memory. We don't have to copy them anymore. That was a weird statement. It's because all of this is about memory, but they're kind of in memory outside of the control of the process. It's an operating system memory. The operating system can deal with memory however it wants. It doesn't have to do any of this stuff. Right? So we can actually keep these separate from the process, but these are in memory. We've stored those. But during a context switch, what do we need to make sure we do? Is we just update which table we're using, and that will change the view of memory for us. Right? If during a context switch I say, I'm running process 1, so I tell the CPU use this page table that's at this address. When I context switch to process 2, I'll say, oh, use the page table at this address instead, and then we have a whole new view of which pages are in which pieces of memory. Okay? So this is, again, adding to the types of things that we need to keep track of when we're switching processes. Before we talked about registers and whatnot. Okay? Now we're doing things like page table pointers and things like that. Okay, these are going to be probably in their own registers as well, these pointers to page tables. So when context switching, you're basically saving that register.
I guess I'm confused on what ed is. Is that the code for the editor?
Yes, that's actual code for the editor. Because,
So it's the same for all 3.
yeah, it's the exact same one.
But the data is different.
The data is different, so so numbered different.
I was thinking it was 3 different users.
Oh, no. These are all the same program, but why do they break it up like that? It's because it's paged. If the editor is bigger than 1 page, we can still do this, right? But anything bigger than the amount of a page, you just have to break up into multiple pages. This example works the same if you just have add 1, 2. Right? Because it's just more clever. It seems more complicated if you make it a 3-page editor. Okay, and also the other nifty thing is that you can break up multiple pages across different frames. Questions on this? This idea of sharing code? Okay, so we're going to look at some more complex ways of mainly storing the page table. Okay, because actually they have a good example, a good breakdown in the book of how these things are related. The size of your pages, the size of your main memory, the size of your logical memory. All of these factors will affect how big your page table is. Okay? And I just want to give you a little bit of an example of how big these get. Your book has something in here about sizes. Okay. Okay, typical, how much memory does an operating system present you with for logical addressing? Right now? Like Windows XP, the current version, how much memory does a program get? Absolutely not. 4 gig, correct.
So that doesn't want, that's maximum CPU support anyway.
No. Why is it 4 gig? Because I've been saying 4 gig a lot, correct. All operating system design originates from what I say in here. No, but why is that?
Isn't that 32-bit architecture?
Because it's a 32-bit operating system. What does that mean?
4 gigs.
4 gigs. 2 to the 32 is 4 gigs. Why is that 4 gig? Because if you were to number the bytes beginning from 0 and count it up 2 to the 32, you'd be at 4 gigs. Okay? So, the logical addressing in this case is from 0 to 2 to the 32, right? So, I lost my page. Okay. Consider a system with a page size of 4K. What is 4K? Any guesses? Okay. Page size. Right? Because a K is 2 to the 10th. Right? So 2 to the 12th is 4K. So, how many entries, how many pages do we have in a book?
How do you know?
That's my question. And
How big
that was the answer. Right? You mumbled it, but I heard the right number. 2 to the 32 divided by the page size if a page is 2 to the 12 big, you can fit that many into 2 to the 32. Right? So, 2 to the 20. It's a fairly big number. How big is that number? Right. It's around, it's around 1 million entries. Pretend each entry consists of 4 bytes.
It's a billion.
Is it a billion? 2 to the 20? You know it's not 2 to the 30 because you can't fit that many.
Yeah. Yeah, 1,040,000.
Let's say 1 million. Alright, so we have 1 million entries. And an entry looks like what? Well, we have, right, a page and a frame, mapping, right? So that's about, how much is a byte? Right? Oh wait, that's good. So, you just say
130 bytes, right?
yeah, per doing it in bytes. So we at least need, what I'm saying is how many bytes do you need to store that? That's about byte and a half. Let's say 2 bytes, or no. 8, 16, it's 4 bytes. Right? About 3 bytes.
The number itself?
Yeah.
Like the 1 million number?
Yeah.
What would you want to store the number?
Are you kidding? The whole exercise is how do we store these numbers? No, I want to store the number 2 to the 20. But that's 2 to the 20, that's basically, that's how many bits we need, right? So it's about 2.5, so about 3 bytes. About 6 bytes. I don't know why they're saying each entry consists of 4 bytes. Oh, we don't have to store the page. Right? Because the page is the index. We just need to store the frame. So each of these is about 4 bytes, right? They're saying 3 bytes. I mean, we can store that in 3, but our processor's using 4-byte integers. We might as well use 4 bytes, right? So 4 bytes per entry, 1 million entries, 4 million bytes, about 4 meg, right, per process. Right? So that's pretty big. It's bigger than most memory that operating systems used to have. Okay? So, if each program needs a page table that's 4 megs big, that's tough. Okay? Plus, if you're going to store the page table in memory, that's even tougher, right? Because now, as soon as you get a handful of programs, that many programs times 4 meg, bad news, right? So what you end up doing is you end up also paging the page tables and whatnot. In other words, you manage the memory that the page tables are using. So some of the ways you can do this are things like doing hierarchical or multi-level pages, or page tables. So in this case, you break up an address into the first part of the address, looking up what page table to look up in an outer page table. Okay? This is sometimes called a page directory. So if you think of it like storing files on, in your computer, you store files in folders, which can then be in folders, and that's how you find what you're looking for, right? You first go through a general core search of what folder you want to get in. You get in that folder, and then there's a number of files you can look through there. In this case, the page directory is a collection of page tables. So you look up which one you need, and then once you found the page table you want, then you go through your normal calculation that we did before to look up what address to go to. Okay, so rather than us doing the direct translation, I don't have it anymore over there, where we go from look up the page and the offset, find out the frame and the offset, and then calculate up. Now what we do is we look at where in the page directory it is. Once we find that, we get the page table, look up the frame. Then we go get the frame, and then we can find out where in physical memory it is. Everybody cool with that? It's just one additional level. Why is this good? Well, each of these page tables, these multiple page tables in the page directory, we have the potential to swap them out to disk and whatnot and not have them using main memory. Okay, we can also sometimes do tricks as to some of those page tables not having to be created at all. You just put an entry in there that it's not there. Right? And you don't have to use any of the memory, which is good because a lot of page tables are, for the most part, empty of data. Because if I'm the operating system and I give you 4 gig to work with, how many of you have written a program where you needed more than 4 gig or even approached 4 gig of memory use, right? Your hello world gets 4 gig, right? When you write hello world in a program, you're assigned 4 gig of memory. All your page entries except for the first one are empty. Right? So rather than allocating all of it, you do something like this.
So this changes that formula, right?
Yes, just like this. See, where now we've broken up the page section of the first one, of the first system, we just break it into 2, right? And use the first part of it to look up what page table to use in the page directory, and then we look up the page in the page table, and then we look up the offset, which is the same on both sides. Okay? So before, where we have this address, right, where we have P for the page entry and D for the offset, this one part, the first part, the P, becomes these 2 parts. Okay? And the second one works exactly the same. The second part of this address works the same. It's looking up in a page table and getting a frame. It's the first leading part that's different because now we're looking up a page in a directory, or a page table in a directory. All right? Everybody cool? Notice this is a 32-bit machine with 1K page size. How do we know that? Even if I didn't tell you this, even if I didn't tell you that this is a 32-bit machine with a 1K page size, how can you tell that just from the addressing scheme? How do I know it's a 32-bit machine? 12 plus 10 plus 10. Add up all the bits. That will give you the total memory size. How do we know that? Well, the whole idea of this was how do I get from a logical address giving us the whole memory to this paged address. So we know we can access any byte in logical memory with 32 bits, right, with the whole address. So that's how you know how big the machine is. How do I know it's a 1K page size? Here's the way you think about this. How would you get, 10. How would you get to a particular address within a page? By using the offset. In other words, the offset is from the beginning of the page, how far in do I go? Well, what's the maximum amount offset I can go according to this address? 10 bits. So if 10 bits is the last byte in that page, I know that the whole page is 2 to the 10th, or 1K. Okay? And then this tells us how we broke up, the page number, the two portions of the page number tells us how we broke up our page table into pieces and put them in a page directory. Okay, so, and you can keep going with this. This is just one of them where they say, look up the outer page, look up what page table we need in the outer page table using the first part. So that will get us an entry saying, oh, your page table is here. So then you go to that page table and then take the second part of the address, right, and look up the entry in the page table. That will give you what? If I look up this entry in the page table, what's referred to me? What's returned? No. What do I get from a page table? You get a frame. You get a frame back. So now that I have the frame, I can go find the frame in physical memory and then use D, the offset, to get the byte in that frame. So I found the page table with the first part of the address, I found the frame with the second part of the address, and I found the byte in physical memory, or in the frame, sorry, with the third part. You see where this is going, right? We could keep going out if we wanted to. Okay? And your trade-off here, as far as how you break this up, what you're trading off here is how big your page tables are versus how quickly you can access an individual byte. If you're not going to look up additional page tables very often, in other words, you're mainly going to be working, if I give you I give you logical addressing of 32 bits, right? We've already said that that's 4 gig, right? And you're writing hello world. And how often are you going to get past the first few pages? Hardly ever, right? So if those first few pages are in their own page table, and that's the only one you'll ever reference, the rest of your page table isn't used at all. But by breaking up the page table like that, I've made it so I have another level of indirection where I have to go look in the page directory and then from there go look at the page table. So there's this trade-off between how much active page table I have in memory and how many steps I have to go through to get there. Okay? You can see how this could get bad where we did the calculations for using the TLB, remember? And how we had a hit ratio and then how often we have to go. This is accessing even more memory, right? Every time we look up in the page table, we're going to have another memory access there, right? So if you're measuring the performance of memory access, each of those memory access is reducing your performance compared to just directly accessing memory. So that's the trade-off here. And on very big operating systems like 64-bit operating systems or even 32-bit when we went to 32-bit, a lot of that memory is not being used, right? So trading off between these is difficult. And even more so is that if you're designing an operating system that can run on different architectures, like for example, if you're Windows, Linux, Mac OS, all their or BSD, all of these different operating systems are running on different architectures these days. Sometimes they're running on 64-bit, sometimes they're running on 32, right? XP can run on 32-bit and 64-bit now. You have two different versions, but the main code base is the same for both, right? Mac OS, they were running on 32-bit, they went to 64, and then they actually bumped back down to 32 when they switched back over to... it's both. Actually, I think the last version was 64 because the PowerPC is 64-bit, or the G5 was, I believe.
Now they're back to
when they went to Intel, they went back to 32-bit, but now that the Core 2 Duos are coming out, those are going to be 64-bit. So you're bouncing back and forth like between these different architectures. There's a huge difference between 2 to the 64 bytes of memory and 2 to the 32 bytes of memory, right? It's not twice as much, it's exponentially as much, right? So the page tables grow with that same speed, okay? So sometimes very clever systems are used to actually make this flexible. Like for example, if you look at your book, they give a good example of Linux where they use kind of a tiered memory access scheme, but for 32-bit operating systems, they make this number 0. What does that do? If I make the middle number 0, I've kind of gone back to just page table and offset, right? Whereas if I expand it out for like 64-bit operating systems, I can break up the page table into a page directory, right? An inner and outer page table. Okay? So, hashed page table. You can imagine what this is. Hashing is what? You put entries into a table using a hash function. Okay? So the hash function will translate your larger number P into a smaller set of hash table entries. And sometimes you'll get collisions where the same number or different numbers hash to the same entry. In those cases, you either have to boot out the old one or you have to make a linked list of the things that are in there or some other mechanism or store more than one value in each entry. Okay? But the idea here is that you store your mappings of logical pages to physical frames using this hash table instead of an array like we were doing in a regular plain hash table. I mean, a page table, in a plain page table.
What's the real difference between a hash, like, other than the array kind of, like,
What's the difference? I mean, what is the main difference? Anybody have a guess? Well, they both have a scheme, right? The arrays is put them one after another.
oh, is this not like an even hash?
No, not in a hash. Okay. An array. If I have 2 to the 32 entries, oh no, I don't have 2 to the 32. I have 2 to the 20 entries. How many entries in my array do I need? I need 2 to the 20, so one after another, right? If the middle 2 to the 10 of my entries are not used, can I just take those entries out of the array? No, because I need that empty space to be, so my indexing is correct, right? Even though I'm not using those entries, I still need a value there so that I can offset from the beginning of the array and find the entry I'm looking for. Okay? A hash table doesn't necessarily do that. A hash table is like mapping an index to any arbitrary location. And you do that through the hash function.
And how would it look for the index? Would it just go to the entire thing?
No, it would just send the index that you're looking for through the hash function again, and that will tell you. In other words, this. I'm looking for page 3. What do? I take 3, I hash it, and it will come out with some other arbitrary number. I don't know what it is. Okay? The key is that it's going to come out with the same number no matter how many times I send 3 through. Okay? 3 maps to 10. Just pulling a number out of thin air. Okay? 3 maps to 10. So, in entry 10 of the hash table, I will put the frame that I need. So now, when something else comes to use that address, page 3, it'll hash 3, look up entry 10, and get the frame. Yeah.
So 10 is always going to be 10 in the hash table, right?
10 is always going to be
10 is
Right.
It might be like 1, 20, 30.
No. I mean, it is the hash table is in order.
Or it's-
What you're doing is this with a hash function, and this is just a general thing with hash functions. Hash funnel is like a big funnel. Okay? You take a big space and you map it into a little space. So for example, 2 to the 20 pages, I can send through and that will become 2 to the 3rd. And I can make this number as small as I want, I can make this number as big as I want. But the trade-off is, okay, here's a hash function. The first 3 bits of the number is my hash function. So any number that I take that's 2 to the 20, I can take the first 3 bits of it, and that's its entry in the 2 to the 3rd table. How big is the 2 to the 3rd table? Right, 8. Eight entries, right? How big is this table? Huge, right? Really big. But any address, I can take the first 3 bits. So let's say I give you a number 1, 1, 0, 1, 0, dot, for 20 different entries, right? For 20 different digits. Okay? So where does that map to? 1, 1, 0, which is what? 5, 6. Yeah, right, 6. 6. 1, 1, 0 is 6. So what do I do? 0, 1, 2, 3, 4, 5, 6. And I put in basically 1, 1, 0 is the index. Then I can put in the frame where that's stored. Okay. So I can hash things like that and then find out where the frame is.
So what if you have another one?
Yeah, then you can start having collisions, and that's bad. Okay, so you either have to boot some out, or you have to have a bit, like some sort of flag saying what can be, what is actually in there, some additional information, or you have to always boot it out or something.
Yeah, what we learned, I don't know if this applies here, is that, I forget the terms, but you either just go to the next one, or you.
But you still need some mechanism to know if the next
So
one
it's
is,
like another function.
or you put a link, you put a bucket
Okay.
in there and you can put multiple things in there. But the idea here is that if you're not going to be accessing a lot of the pages on this side, then you can get away with having less data to store it in because it's sparse. In other words, a lot of the entries are empty. So in this case, what you're doing usually with a hash table is you're making it so that you don't use space for the empty area. Right? You're trying to use just a little bit of, you're just using enough space to hold the real data. Okay. So arrays, very inefficient in how you store things if there's not a lot of data in it, right? Or not a lot of active data in it. Okay. A linked list, great for storing data if great for the amount of space it takes for sparse data, because you only have enough memory for just the data you're looking for plus the pointers to the next entries. A hash table is somewhere in between that. You're actually using more space than your amount of data because you have to have more space because there's going to be some misses, right? Some stuff that things don't hash to. You're hardly ever going to have a perfectly filled hash table, right? There's not a lot of probability that every number that you send into it in hash will map to a different, right? Because if you don't want any collisions, a collision is when two numbers hash to the same value using the hash function. If you don't want any collisions, that means your space has to be very big so that they don't run into each other. But in that case, you're wasting a lot of space, right? Because a lot of those are empty. If you don't want to waste any space, then you're going to have a lot of collisions, so then you'll have buckets there that you have to search through. And if it's perfectly filled, chances are there's a lot of collisions. So that's the idea behind this hashed page table idea. Inverted page table. This is kind of a funny way of doing things. Here what they do is they put an entry for every frame. And then what's in the entry is what page is stored in the frame. What does this tell you about how we can look up entries in this type of page table? Normally, what information is in our address, our logical address? We have a page and an offset. Page and an offset. We have 4 frames, and what they're saying with an inverted page table is we will always have 4 entries in the table. So in this case, the index is the frame. Now, how do I look up? What am I trying to get in place of the page? I'm trying to find out what frame it's in, right? How would I find that in this table? Search how? Right? I mean, not however we want. There's one way to look up. It's exhaustive search, right?
You have the page now, right?
I have the page.
And you have pages in there.
I have pages in there.
Just look that up. And you have frame too.
How do I look it up?
Sequential.
Sequential search. I have to exhaust the search. I have to linear search. Do you know, were we doing that before? No. What were we doing before? This is inverted. Okay? Regular page table is what? As big as the logical address space. So big. But what is the index? Pages. Right? We can look up pages by random access directly. In other words, we've sorted the pages and we can look through them. We can get the frame directly. This is different because we're doing linear search through the frame, and there's nothing else we can do about it.
I mean, you have to start at the beginning, you can't do like the log in search.
They're not sorted.
They're not sorted in.
The data you're looking
Oh,
for is
right.
not sorted, right? Okay, and we have to exhaust the search. Or we have to do exhaustive search.
So what are the advantages there?
What is the advantage? It's obviously not speed, right?
Reliability.
It's not any more reliable. Hopefully both of these are completely reliable.
You only need one table?
Yeah, that's one. Well, then we need more data in the entry, like saying what process it belongs to. I mean, we'd still probably want one for each process. But the key is this. How big is this table? How big is this? How about this? How big is this table compared to? How big is the inverted page table versus a page table? No. Why not?
Because you have the same amount of page entries, don't you?
No.
It's gotta be bigger.
What is?
The physical, or the frame, the inverted page table's gotta be bigger.
No. All right, there. You got your answer, right? Through elimination, it's okay. If the inverted frame table, or the frame table, right, the inverted page table, if that is bigger than the page table, you probably don't need any of this fancy memory management stuff. Okay? If I'm giving you 4 gig, for example, as a program, Do you have to have 4 gig of physical memory to run it? Not necessarily, right? I'll do tricks. Right? Chances are your physical memory is a lot smaller than your logical memory. Okay? The key is this. This inverted page table is just as big as your physical memory. Or, I mean, that's how many entries are in it. Or however many pages you can, how many frames you can fit in physical memory. And this will remain constant. This is, the page table is usually a lot bigger. Right? Because it's going to be on the scale of like 2 to the 32, right? Whereas the frame table is going to be physical memory divided by frame size. Okay? So the key benefit to inverted page table is size. Inverted page table, again, you have the physical frame is the key, this I. So when you're looking up using a logical address, you have to actually linearly search through and find. In this case, they're putting the process ID and the page, which is, like what Lizzie suggested, just having one for all the programs. Which can make sense because there's never going to be more allocated pages than you have frames. It's impossible. Okay, so this kind of maps directly to your physical memory, which is good in that it's small, but this search is horrible. Okay. Okay, and then finally we have segmentation. I'm just going to briefly look at this. Segmentation is a little bit more like what we saw at the beginning, where we have a base and a limit. Does anybody remember what a base and a limit is? This is for contiguous memory mapping. Okay? A base and a limit says that if I give you a base and a limit, and you have logical addresses, you find the logical address by taking the logical address and adding base to it, and that will be your physical address. And what's limit? Limit means you can't ever go beyond that physical address of limit. In other words, the physical limit is how high you can go. In other words, base is the beginning, then limit is the end. And all your logical addressing maps into the space in between. Okay? Segmenting is a way of giving individual pieces of a program a continuous view of their memory. Okay? So what they try to do is they might break the user program into these pieces which represent kind of logical pieces of the program, the stack, functions, the main program, variables, things like that, okay? You take those pieces, break them into blocks, and then you can allocate the blocks into main memory. Okay, so it's kind of a logical type of paging. I mean, it's a paging according to the semantics of the data you're breaking up, as opposed to arbitrary fixed sizes. Okay, so how do you find it? Well, you have a table which will give you the base and limit for a given segment number. So your address is a segment number and then an offset. You look up in the segment table using the segment number to find the base and limit. In other words, the chunk of memory allocated to this segment. And then you look offset amount past the base, and that's where your physical address is. Okay? Segment table base registers points to the segment table location in memory, and the segment table length register says how long that segment table is. These are just registers that point to the segment table. Okay? Each segment you can do additional, give additional information like whether you can read, write, or execute in those pieces of information. And anytime you do something wrong, you can trap to the operating system. If we get to outside the limit of a segment, we try to do an operation we're not allowed to. But then we get to the same problem that we saw with contiguous memory of allocating the whole segment into memory, and how do we fit it in, and the fragmentation problems that occur. But this hardware is showing that we can take a segment number and an offset. We look up the segment in the segment table, check the limit and the base. If our offset, right, violates our limit, we can trap and say, no good, you can't use that address. Or we can allow it through, we add that to the base, and then we're in physical memory. Okay. It's just add this much to the beginning before you look at the offset. Add the base before you get to the offset, and check to make sure you're not past the limit. Okay. And that's where I want to end, is on segmentation. Segmentation is an interesting. I mean, it's a scheme that we used to program directly with segments on older, like Intel boxes. You actually laid out your memory in segments, and you can directly program in segments, which was fine on an individual user operating system. You just have your segments, and then you can lay out your code logic. I mean, how you created your code was logical. I mean, you said, well, this function is in this segment, so I can just call the beginning of that segment. I don't care where it actually ends up being in memory. Okay. Later on, we start getting to a flat addressing with like paging and things, which becomes very useful. And these days now, typically, the two schemes of segmentation and paging are usually combined. Okay, like a good example, and I'm going to leave it to you to look at this in your book. Is look at the example of the Intel Pentium. Okay, in your book, they tell you how both of these schemes are supported, and then they have an example of how you do that, how you use those two styles with Linux. What Linux does is it breaks up things like the kernel code, kernel data, user code, user program space, and all that stuff. It breaks those up into segments, and then each of those segments has a view of the memory using a page table. Okay, so user programs have a view of the memory as just one flat paged addressing, but that's just one segment that they get to see. The kernel has other views of the memory, which are a different segment, and then within that segment, they see it as pages. Okay, so we're done with the different styles of memory management, but look in your book and read the example of both Pentium showing you how the hardware can support these schemes, and then Linux on the Pentium, which says how can you utilize this hardware in an operating system. Okay, but really understand these different schemes. Okay, the example of Linux on the Pentium is to give you a practical frame of reference for why any of this stuff is even useful. Okay, but know the schemes and know the drawbacks, the benefits and drawbacks of each of them. Okay, why you choose one over the other. I put up a few questions for homework, and I just posted those up, so those should be out on WebCT. It's just a few questions, kind of like the last homework, because they're both kind of halves.